Alrighty, hello there. We're going to be looking at section 11.3, and in 11.3 we're going to be using limits to investigate what is known as the tangent line problem. And this is really where we start getting into the calculus stuff. So calculus is a branch of math, and calculus is all about studying the rate of change of functions. We've already talked about that slope, that when you find slope, that's the rate at which a line rises or falls. For a linear graph, the slope is the same at every point. But for graphs that aren't linear, so when they're not linear, the rate at which the graph rises or falls changes from point to point. So, for example, like this function right here, like this, notice, is decreasing. This, at this point, that function is increasing. So notice there are a lot of different slopes that would have. And so to determine that rate at which a graph rises or falls at a single point, what you can do is find the slope of the tangent line at that point. So again, we're going to say that the tangent line is the line that best approximates the slope of the graph at that point. And those lines that I just drew and erased, and these lines here are tangent lines, and those are going to estimate the slope. But notice that that changes as you go throughout the function. So tangent lines to non-circular graphs can intersect the graph at more than one point. So notice if we extend this tangent line, it does end up extending it down here too, but we just kind of got to take that with it. So because a tangent line approximates the slope of a graph at a point, the problem of finding the slope of a graph at a point becomes a problem of just finding the slope of a tangent line. But this is hard to do visually. I can see that in this third graph, that looks like that has a slope of 0 at that point P. But what if I wanted to do it at a different point P? So because it's hard to do visually, a more systematic or precise method is using a secant line through the point of tangency and a second point on the graph. And then eventually, we're going to put the limit process into this also, okay? So let's review what a secant line is. A secant line is a line that intersects a curve. So it's a line that intersects the curve in at least 2 points. And over here we have a graph, and we have 2 points that are marked. And I'm going to call one of these points X, and then the output would be f of X. And so that's where that is on the graph. And then what I'm going to do is I'm going to move a certain amount over, and I'm just going to arbitrarily call that H. So if this was when X is X, and we're moving H units over, then that means that this point has an X coordinate of whatever X plus H was. And then the value of the function, then of course we would put X plus H in as that input. And so then the secant line would be the line that goes through those 2 points. That would be that secant line, okay? And so remember that we know that slope, when we had a linear equation, was y2 minus y1 over x2 minus x1. And so if we want the slope of this secant line, then we would take our y2 minus y1. So our y2 is f of x plus h minus our y1 is f of x over x2 minus x1. So our x2 is x plus h. Our x1 is x. We subtract. And we can see that that's how this is, they came up with this, that slope of the secant line, is that it's f of x plus h minus f of x over h. Notice that this is also what we have talked about as the difference quotient. So this difference quotient is actually that slope of a secant line, okay? So that's kind of the idea. Now, you might be saying, okay, Mackie, like this secant line connects 2 points, but it's not a tangent line. So here's how we get to that idea of the tangent line. Let's make this value of h get smaller and smaller and smaller, okay? So choosing the second point closer to the point of tangency gives you a better approximation to the slope of the tangent line. So notice in these series of drawings, notice that this h value is getting smaller. So here h was this big, h is getting smaller, smaller, until it goes to 0. And notice that then that secant line gets closer and closer to that actual tangent line, okay? And that's kind of where we get to the limit. So as h approaches 0, the secant line approaches the tangent line. That's what these pictures suggest, okay? And then using the limit process, we can find the exact slope of the tangent line at a certain point. And that's kind of what we're going to be doing in this section, is we're going to use this idea that we're going to let that h get closer and closer and closer to 0. And then if it was able to be 0, notice that we would get that tangent line. So using the limit process, we're going to find the exact slope of a tangent line, okay? So that's kind of where we go from the idea of the secant line to the tangent line, okay? So when we talk about the slope of the graph, anytime it says to find the slope, that just basically means to use that formula. So what we say is that we're going to say that the slope of a graph is going to be the limit as h goes to 0 of the slope of the secant line, okay? But remember, we defined the slope of the secant line as that difference quotient, f of x plus h minus f of x over h. And this is all provided that the limit exists at that point. Then you're going to be able to find the slope of the graph at that point. So again, when it says, a problem says to find the slope, it basically means to take the limit as h goes to 0 of that difference quotient. Okay, and again, this is the difference quotient. The difference quotient is that slope of the secant line, and the slope of the tangent line is what happens when we take the limit as h goes to 0. Okay, so there are a couple ways that you can do this. If you look at my filled in notes, which I'll do here, I don't like writing limit as h goes to 0 8,000 times. I prefer only 5,000. So what I often do is I find the slope of the secant line, simplify that, and then I do the limit part to it, okay? So this wants us to find the slope at the given point, and it gives us f of x equals x squared, so that's our rule. And it wants us to find the slope at -2, 4. And so because they give us a point, this is asking us to find the difference quotient at x equals -2. Okay? So the first thing I'm going to do, and again, I'm going to just find the slope of the secant line, and then I'm going to take the limit of that. You can put the limit in front the whole time, and then you don't have to use that notation. I'm just trying to avoid writing the limit all the time. Okay, so if we want to find the slope of the secant line, what we need to do is we need to find f of x plus h. Well, our x is -2. So f of -2 plus h minus f of x. And remember, our x here is -2. And then over h. And then we can simplify that a little bit. We can say, so if we took f of -2 plus h, that means that in place of x, we are putting in -2 plus h. So that would be -2 plus h squared minus, and now we want to find f of -2, so that would be -2 squared, and then all over h. So again, this is my f of x plus h, this is my f of x. And then we can just flesh that out a little bit. So if I square -2 plus h, I get 4 minus 4h plus h squared minus, and if I square -2, I get 4, and then we have that all over h. We can see that these 4's are going to cancel, and I would be left with -4h plus h squared over h. And I can see I can take an h out up top. And then that's really handy because I factored an h out of the numerator, I can then simplify, and I see that this slope of the secant is given by -4 plus h, or h minus 4. Okay? So if you started just by finding the slope of the secant, then the next thing you have to do is take the limit as h goes to 0 of that slope that you just found. Okay? You could have written limit as h goes to 0 in front of each of these expressions. Again, I'm just trying to save a little bit of work here. All right, so because of this, this is something that we're able to use direct substitution for. There's not an issue, it's not in an indeterminate form, so we can just say, all right, let's put 0 in for h, and we see that the limit as h goes to 0 of h minus 4 is -4. So that means that the slope is going to be -4 at the point -2, 4. So if we were to graph that equation, and then we were to find the slope at -2, 4, that slope would be pretty much equal to -4. Okay? Okay, let's do another. Find the slope and the equation of the tangent line at the given point. So again, they give us a specific point. They want us to find, let me move this up. They want us to find the slope at 2, f of 2. And so this basically means here that I want to find the difference quotient, again, at x equals +2, since that was the x value that they gave you. So I'm going to start by finding the slope of the secant line, and that is going to be f of x plus h, so f of 2 plus h, minus f of x, which will be f of 2, and then over h. So now we have to use this function. Notice this one's a little bit more complicated. So to find f of 2 plus h, I need to put 2 plus h in for x. So x squared plus x now turns into 2 plus h squared plus 2 plus h. And then we're going to subtract f of 2, which means we would have 2 squared plus 2. And all of that is over h. So then we can simplify that a little bit. So we get 4 plus 4h plus h squared plus 2 plus h. And then if I do this, 2 squared is 4 plus 2 is 6. So this is really -6. And then all over h. So if I look here, I notice I have +4, +2, and a -6. That cancels out. So I end up with h squared plus 5h over h. I can factor an h out of the numerator and again cancel, and I find that the slope of the secant line is given by h plus 5. So again, what I found was the slope of the secant line. In order for it to be the slope of the tangent line, I have to take the limit as h goes to 0 of that secant line. And again, if you don't want like a step 1, step 2, you can have a limit as h goes to 0 in front of every single step. But like on the AP exam, they take off if you don't have that and you're finding the slope of the tangent line. So just make sure that if you don't label that as the slope of the secant, you have to have the limit the whole way through, okay? So then again, this isn't in an indeterminate form, so we can use direct substitution, and I find that our slope is 5. Well, this not only wanted the slope, this one wanted us to have some extra fun and to find the whole equation of the tangent line. So remember that the tangent is linear, so because that tangent line is linear, we can use point slope form, which is y minus y1 equals m times x, the quantity x minus x1. And we know that our x is 2, but notice that they didn't really tell us what f of 2 was. So just to find f of 2, we can just substitute that in, and we actually found over here that f of 2 was 6. So basically we're going to use the slope of 5 and then the 0.26 and then write our equation. So we'd have y minus 6 equals our slope of the tangent line m times the quantity x minus 2, and then we can distribute and isolate y, okay, and then we end up with y equals 5x minus 4. So that's finding that equation of the tangent line. So we use the slope and then use that slope to do the same thing on the tangent line. As far as verifying the results on the graphing calculator, what you would do for something like that is in y1, oops, let me clear all this stuff out. In y1, we could put the equation x squared plus x. And then what we can do is, just to kind of make it a little bit different, this suggests that we do zoom decimal, which is number 4. And then what we can do is go to the draw menu. So if we do second program, that brings us to this draw menu. And then we can draw the tangent line, number 5. And then we can just type the number 2 to tell us that we want it to draw it at x equals 2. And notice it draws that line. And notice that you can see 1, 2, 3, 4, the y-intercept's at -4. 1, 2, 3, 4, 5, 1, and it looks like it has a slope of 5. So that's super fun. But we can't use graphing calculators on a test, so I guess that's just to check your work. All right, so let's try example 3, where they want you to find the slope of f of x equals the square root of x. So again, what we want to do, they didn't give us a point, so when there's no point given, which is actually what you're going to be seeing more of going forward, just leave x as x instead of substituting a value in. So in step 1, if we're doing it this way, we find the slope of the secant line, and remember that this is going to be f of x plus h minus f of x over h. And in this problem, f of x plus h means we'd put x plus h in for x, so the square root of x plus h minus the square root of x, since that's f of x, over h. And in this particular problem, if I'm looking at the slope of the secant line, there's like nothing really to do there. So that means that the next thing I would do is find the limit as h goes to 0 of the slope of the secant line, which we found to be the expression, the square root of x plus h minus the square root of x over h. Now the problem with this one is that this is in an indeterminate form, and so now we're going to have to make this such that we can take the limit as h goes to 0 and use the methods of the previous section. So notice that if we tried direct substitution, we would be dividing by 0, which would be an issue. So one tactic would be to rationalize the numerator. So what we can do is multiply by the conjugate of the numerator, multiply by root x plus h plus root x in both numerator and denominator, and see if that can help us out a little bit. So what we get there is we end up getting that this is going to be just x plus h. The outer and inner cancel. So minus root x times root x would just be x. And then we have all of this in the denominator, h plus root x plus h plus root x. We can then see that these x's are going to cancel, and we're left then with the limit as h goes to 0 of h over h times the square root of x plus h plus the square root of x, and we can see that the h's cancel, and so basically we have the limit as h goes to 0, let me see, of 1, and then over the square root of x plus h plus root x. So by rationalizing the numerator, we were able to get this into a form where now we can use the direct substitution, because now we don't get a denominator of 0. So if I put 0 in, then I end up with the square root of x plus 0 plus the square root of x in the denominator. So that's just 1 over root x plus root x, and that is 2 root x down there. And you guys will see that we don't rationalize the denominators once we find a lot of these, and so we're just going to say that that's our slope. So an expression for the slope of that line is going to be 1 over 2 root x. And this is really what we're going to be seeing more of, where we leave x as x instead of being given a specific point. Okay. And that's what it talks about next. Did you look at the difference between the setup in the last two examples? In examples 1 and 2, we found the slope at a specific point using this form of the difference quotient, where notice that we have like a specific value in place of x. And when we have a specific point, that's when you're going to be able to get that your slope is a specific value. Versus in example 3, which again you'll find more often, we're finding the slope at any point. And when that happens, you're going to get an expression. And then the nice thing about getting an expression for the slope is that then you can find the slope at any point. So for example, where'd my paper go? Oh, here. So for example, if we wanted to find the slope of this at x equals 1, then we could just substitute 1 into that expression. If we wanted to find the slope of that at x equals 9, we could just substitute 9 into that expression. So that's usually why we do this instead. We find like a general equation, and then we find the value for different values. And that's what we'll do in example 4. It wants us to find a formula for the slope of the graph f of x equals x squared plus 1. So we're going to use it at any point to start. And then we can find the slope at these different points. Okay, so again, I'm going to start by, for this, just finding the slope of the secant line, just so there's not as many limits that I'm going to be writing. So that means I'm going to find f of x plus h. And so f of x plus h means I'd put x plus h in for x. So I have x plus h squared plus 1 minus f of x, which is x plus 1, x squared plus 1, and then all over h. So if we flesh that out, I get x squared plus 2xh plus h squared, and then plus 1. And then I can distribute this -2, negative x squared minus 1, all over h, and let's see what cancels. So up here I've got the x squareds, the 1s, and here I can see that I have 2xh plus h squared. To save a little bit of time, I can factor an h out to get h times 2x plus h over h. Then those h's cancel, so I have the slope of the secant line being 2x plus h. So then technically, to find the slope of the tangent line, I'm going to take the limit as h goes to 0 of 2x plus h, and this is a form that we can use direct substitution. So I'll just say that's 2x plus 0, which is 2x. So that means that my slope of the tangent line is going to be 2x. So that's what they wanted us to do first. Okay? Now they want the slope at 2 specific points. So in step 3, I'll call 3a, let's find the slope at -1, 2. Well, the slope is going to be 2 times whatever x is. And here our x is -1. So our slope is -2. So our slope is -2. And remember, this is the point it's going through. So then we're going to use point slope form using this slope and this point. So I have y minus 2 equals -2 times x minus -1. And then I can distribute, and I find that the equation is going to be y equals -2x. And you can see from this graph, here's the graph of the original equation, and then there's the point -1, 2, and then here's that tangent line. Notice that that's the graph y equals -2x. So that's the equation of that tangent line. Oh, I guess it just wanted the slope, didn't it? I got excited. So there's the slope. We're just going to do this because we're bored. Just kidding. Okay, so let's do example 3b. In example 3b, we're going to find the slope at 2, 5. So our slope is going to be 2 times x, and here our x value is 2. So our slope is 4. And so I guess that's the answer to the question, but I'm having a lot of fun writing these linear equations. So if I were to be asked for the equation of the tangent line, then I would just put those all in, and I'd find that it's y equals 4x minus 3, and you can tell from this little picture that that is pretty similar there. Okay? So in example 4, the derived function that we got, that m equals 2x, we said that that represents the slope of the graph f at the point x, f of x. This derived function is called the derivative of f at x. That's right, we're finding derivatives, we're doing calculus, this is exciting, okay? So what you're going to find is that we have this f prime of x, that's how that's read. And there are several different notations for this. This notation is from this dude named Lagrange. So Lagrange's notation is f prime of x. That's one of my favorite notations. And then this dy dx was actually from this guy called Leibniz. These two are probably the most common notations. Oh, can you even see what I'm writing? Sorry. that these are the most common notations that you'll see. I actually see this an awful lot in our textbook, but this is less preferred because there is no variable, like no other variable, like because you don't know if you're differentiating with respect to x or with respect to t. You'll see what we mean going forward. This is actually this d, capital D sub x, y, I like never see that. But that was Euler's notation. And just a little fun fact, a little y with a little dot over it, that's Newton's notation. This is kind of like an extension of Leibniz's. This is kind of like an extension of Lagrange's. It's just with the one variable instead of with the two. So anyway, what we found is that because this derivative is the same as that slope of the tangent line, that's going to be our formula for the derivative. So the derivative of f at x is f prime of x, which is the derivative of f at x. And all we do is we just take the limit as h goes to 0 of that difference quotient, or of the secant line. So the derivative is the tangent line. The derivative is the slope of the tangent line. Like these are all the same thing. So again, the derivative is simply a formula for the slope of the tangent line. That's it. So again, this is always provided that the limit exists. Okay? And this is Cauchy, and like a nice picture of him. It looks like he needs the sun a little bit. Anyway, he is the one that defined the derivative. So thanks for giving us something to do. Okay? And that is it for day 1. Let me know if you have any specific questions. Day 2 to come.